Okay, I'm talking about Haworth projections now. So Haworth projection is a two-dimensional structural notation showing the three-dimensional picture of a cyclic form of a monosaccharide. So a guy named Walter Haworth. What we do is we view the hemiacetal ring system edge on. So this close to us is thick to indicate that the ring is laying down. We're looking at it flat. It's kind of going away from us like that. So it's like a disc that we're looking at the bottom of. And the oxygen is always, for a six-membered ring, the oxygen is always at the top right, and for a five-membered ring, the oxygen is always straight at the top. Now, I've numbered these 1, 2, 3, 4, but that doesn't always mean those are going to be the strict carbon numbers. But there will be 4 carbons and 1 oxygen in a 5-membered ring, and 5 carbons and an oxygen in a 6-membered ring. Now, the first thing we do is we can determine the L or D form of a monosaccharide by where that last CH2OH group goes. D form is above the ring, L form is below the ring. Now, I want you to understand that this is coming from the Fisher projection. So remember, the L form, the other thing I want you to be clear on is that, let's say that this is, actually I guess I'll have to clear this up later, but the L form is going to be, the L form has the hydroxyl group at the bottom, or that hydroxyl group, the carbon group at the bottom and the D form at the top. Now this is just coming from looking at the Fisher projection. So CHO, when we look at all of the things here, if it's on the right, so this means D, which means that this group is on top. So this OH group isn't really represented as an OH group in the Fisher projection because this is the oxygen from here. So the only thing indicating the chirality here is this CH2OH group. That's how we show it. So L form, D form, L form. And this gives us a frame of reference for all the other chiral centers in the ring. Alpha and beta are determined by whether or not that OH group on the first carbon relative to the oxygen is on the same side or the opposite side as the last CH2OH group. So here, ignoring everything else about it, this first one, this is a beta D monosaccharide. I know it's D because that last carbon is up off of the ring. And the OH group they're opposite each other, so that means that it's beta. Wait, not beta. I did this wrong, didn't I? I'm going to have to relabel these. This is alpha D monosaccharide. Here, this is still D, but they're on the same side. So this is beta D monosaccharide. My goodness. Here, this is all messed up. Let's take a look at these. Determine what these are. This one is L, and since it's on the same side as the hydroxyl group, that's beta L monosaccharide. Now this is a D monosaccharide. This is unspecific. It's not clear as to which it is. So I definitely apologize for having these all messed up. But I want you to realize alpha means opposite. Beta, same side. So alpha doesn't mean that the hydroxyl group is always going to be up or down specifically. It's relative to that last carbon group. Now, if we look at the Fisher projection, all right, I'm going to just draw one sort of at random. Okay, so I'm going to do OH. Okay, so when we look at this Fisher projection over here on the left, you should realize that it's an L monosaccharide from here. So I'm going to draw my ring, and I'm going to count how many are in it. So carbon 1, 2, 3, 4, 5, and the oxygen makes 6. So there's 6 members in the ring. Because it's an L monosaccharide, my CH2OH group is going down. Now, I'm not specifying whether this is alpha or beta, so I'm just going to draw a squiggle line and an OH. This makes it unspecific. This is neither particularly alpha or beta, which you're going to see a lot. Because remember, the chain opens and it goes between alpha and beta in solution. So you can get both. But to do the other hydroxyl groups, any group, so realize this first one is taken care of by the alpha and beta. It's this carbon. It's not this first one. This one is this one. This one is this one. And this one is this one. So if I look at that blue one, the hydroxyl group is going to the right. Anything going to the right ends up going down. I always think of it as pushing the structure over to the right so that it falls so the OH is down. The second OH, and the red one, is also down, but this last one is up because it's to the left. Left is up, right is down. Now, something that's really important to understand. This is what I was about to talk about earlier, but didn't end up doing it. This is the L enantiomer. Realize that the D enantiomer of the same structure, of the same carbohydrate, yes, it is going to have this sticking up, but because every single chiral center has to be different, they will all be flipped. Right? Not just the last one. This is the D of the same thing.